let us now go back to the. Well, actually, we have been always working now with the waterways, and let us today work on quadrature breeze equation. So just a moment. I might need a few times consult here on our notes, which are already include things what we are going to do today. And so when I derive deep water waves, then I said that if we have perturbation going on the surface as e to the power pi kx, then into the depths it must be perturbation must go into the depths like e plus minus k y, the same k but without exponent, so say a decay. And then we selected only the decaying branch if we had infinitely deep water. But if the water isn't infinitely deep, then let us say if we consider displacement of a particle here, it must be zero. But if we take decaying exponent, it is not zero. So you need to do something with it. So instead of that guy here, you need to combine two contributions, both with plus and with minus, so that displacement at this line here, let's be y equal to 0 now, the bottom. Then displacement must be here 0, so it means the expression what you'll be having is hyperbolic sinus now. So like if we have a displacement of a particle psi upwards, let us say psi becomes equal to the amplitude up there, then we have something like psi equals hyperbolic sinus, I think, because sinus goes to 0 at the bottom, right? Hyperbolic sinus of k times y, but then it needs to be normalized at the surface, so we divide it by hyperbolic sinus of k and h, something like that. So that's a substitution what we need to make. And if we do all the maths, we are not going to do all the maths right now. Then what we obtained before for omega square equals g times k, wasn't it? Now we'll be having something like correction from that hyperbolic sinus thing, just to not to make mistakes. So we have now added here hyperbolic tangent. So if you do all the maths, then those derivatives become derivatives hyperbolic cosine and so on. So it becomes hyperbolic tangent of k times h, something like that. So that is the modified dispersion relationship in that case.
Well, what is h?
H is the depth. H is the depth of the water.
Depth calculated from the okay.
All right. So basically, you need to repeat the same steps as we did before. You need to calculate kinetic energy, potential energy, but now we used to have E minus K, E minus Ky by modulus, so decaying branch we used to have. And then, so how we did it? We calculated from here kinetic energy for a component of a wave vector K. So let us say if we had y equals h plus eta as a function of x, and then we take h of x as h of k e I k x, and then we calculate here now t as a function of eta k derivative, and we calculate potential energy as a function of eta k, and then from here you take Lagrangian, and from here you obtain equation of motion d over dt of d Lagrangian over d eta k derivative equals m d Lagrangian over d eta k. That's how we obtain the equation of motion, right? And from here we obtain omega as a function of k. These were the steps. Now what we need to do is we need to do the same steps, but when we previously took that the perturbation vanish xi displacement of vectors, displacement vector is proportional to E minus K y modulus. Now this goes to hyperbolic sinus of K y, and repeat the same steps. So if you repeat the same steps, then you should obtain something like that. We are skipping those steps. But it's like technically you should, it is not that difficult because potential energy expression remains exactly the same. You will be having a little difference in kinetic energy expression now, because it is not exponent of ky, but it is hyperbolic sinus. And then now you remember what we did. So we had, if we had a special relationship, then actually we can go also back to a differential equation. And the procedure was that omega goes, I omega corresponds to d over dt minus I omega, and I k corresponds to I k corresponds to d over dx. That was the procedure. And now we do the same thing, but before, now this is like exact. And you can actually verify if this covers our expressions. So hyperbolic tangent, if kih goes to infinity, then hyperbolic tangent of kh goes to unity, right? Because it's hyperbolic sine of cosine divided by cosine. So this becomes omega square is gk, which is the deep water case, right? On the other hand, if we have a very small h, kh goes to 0, and then we have tangent hyperbolic goes to approximately to just kh, so that we will be having omega square equals g k square and h, which means that omega over k is square root of gh, also the same result what we had. I think we did have like shallow water waves propagate with this speed, didn't we? We did it, right?
Mhm.
Yeah. So this covers the both cases, as you can see. But now what we'll be doing here is we take approximate result for long wave case, K8 goes to 0. But we include here also first correction. So here we just took it like only one term in the Taylor expansion, but now we take two terms. And in that case, tangent hyperbolic equals, now what it is again, KH. Okay, let me write maybe what we know. We know that this is hyperbolic sinus KH divided by hyperbolic cosine of KH. And this is approximately 1 KH plus KH plus KH cubed divided by 6. And divided by 1 plus KH KH squared divided by 2. Something like that. Is it okay? Because if you had sinus, it would be 1 plus 6 cubed over 6 plus x fifth over 120 and so on. With signs alternating. This is minus, x is plus. And here we have just the same signs everywhere. So that makes what's making Taylor expansion of hyperbolic and non-hyperbolic trigonometric functions. And now this is KH and multiplied by 1 plus KH squared divided by 6 multiplied by, and this is 1 minus KH squared divided by 2. We open the braces and keep only quadratic terms. This becomes KH and 1 plus minus KH squared divided by 2 plus KH squared over 6. So this is minus KH over 3, isn't it? And so this is our Taylor expansion for hyperbolic tangent. And so now our expansion relationship becomes omega square equals gk square h 1 minus k square h square divided by 3. And now we take square root of it. From here, omega equals plus minus square root of gh. This is the shallow water wave speed times k. And this becomes square root of 1 minus x is 1 minus x over 2. So this becomes 1 minus k square h square over 6. And Now we make this substitution I omega over d over dt. But we need to think what we do with that plus minus. Let me just verify if at Juhan slide everything is okay. Juhan, sinu pool on kõik hästi, näed ja kuuled kõike või?
Näen, kuulen kõike hästi.
Väga hea. So if we did not take the plus minus, then that omega square would have been minus d square over dt square. That would have been minus x square over dx square. And then we would have a second order wave equation, so called a hyperbolic equation for whatever we have, the height or speed of particles. So if we take speed of particles, it would have been d square v over dt square equals c, the speed, which is, if we denote c as square root of gh, then it would be c square d square v over dx square, and then possibly that second term as well, which goes now as k squared, and so this would be minus again the same c squared divided by 3 d fourth v over dx over 4. But right now we can actually solve starting from this expression we took square root. So if we take this as a basis, then actually we can separate left propagating waves and right propagating waves. Because here, if we take plus, wave propagates from left to right, and if we take minus, wave propagates from right to left. So if we select here only one sign, then we have actually separated the two types of waves. This includes both. But if we separate from here, then we would have, let me write it again, omega equals square c k 1 minus k square h square over 6. And then from here, if we take the same thing, that's we substitute with I and derivative, so it becomes minus I d over dt of okay, if this is in our substitution rule, I wrote it somewhere. Yeah, here. If this is that way, then actually omega corresponds to now we divide by minus I, which is same as plus multiply by plus I, it becomes I d over dt. So see, here is no minus, it's plus. I d over dt of, let us say, b, the speed of fluid particles, and this equals c, that k is another I. This is, but this is now minus I d over dx. And then v, and then there is k square h square over 6, which actually now k cubed. So if that minus becomes plus once we take a plug I into it, so this becomes I cubed. So it becomes one additional minus appears, so we have still minus. We have still minus I h square over 6 and d cubed v over dx cubed, because now we have k cubed here, right? So that is now our equation. And this guy here corresponds to dispersion, meaning that omega over k depending on wave vector k. We say dispersion, so we mean that the speed depends on k, or wavelength of frequency. And now if we divide here everywhere by I and bring things together, then we have equation dv over dt plus c dv over dx and plus c h cube over 6 and dqb over the x cube equals 0. Now, this is still a linear equation, and it cannot be anything else because we have been working with Fourier components and substitution rule based on Fourier. Because if we have nonlinear equations, then it would be not so easy to go from Fourier space to real space and the other way around, because in that case it would include convolution. What we'd like to do is to understand still how we can put some nonlinearity in it, because in real life usually things are nonlinear. So there are some things which still remains linear, but in most cases you have some nonlinearity actually. And so if we think, let me take new page. It's going perhaps too long already. So if we take here away. So here we have deeper water. And so in deeper, we learned that actually the wave propagation speed is here, c is square root of g times h, right? But over here we have deeper water, right? Here is h plus eta, where eta is the amplitude. So actually here over there it would be h plus eta now. And eta, you can consider eta as a current value of the depth, the current value of the height. So that would become now square root of gh and multiplied by 1 plus eta divided by 2 h, if we take here again Taylor expansion of it. So we'll be seeing that our propagation speed of the wave becomes now dependent on the amplitude. So now let us go back and forget about dispersion, but just in terms of the wave propagation speed. So what we had without dispersion was that, let us say, it goes for v and h, doesn't matter. So if you write it for h, our equation for the wave which that propagates in one way, if you don't remember, you can just check what it was. It was this guy here, but we keep only the non-dispersion part here. But that c now becomes a function of depth, or because depth is related to velocity, we can say that it becomes related to velocity. But let us write here for the depth for the time being. So dh over dt equals c. Let me see. Yeah, I had everything in the same side, so not equals to but plus. Doesn't matter in a sense that if I change sign, I go from left propagating wave to right propagating wave. There is not that big difference, but let us keep the same as it was. C dh over dt. But now we have here this part here. And right, sorry. It was not for h, but it was for eta. H is depth, but eta is the height. Let me fix this. Eta. And now we have this term here, which is plus square root of g divided by h, 1/2 g divided by h, and eta over dx equal to 0. So what I did, I was just plug instead of c this corrected value from here, right? This is in your propagation speed. So that equation here basically tells this part here tells that we have a constant v remains constant in co-moving frame. Let me do it here in this slide here. So we had without expansion, we had dv over dt plus c dv over dx equals constant. Similarly, d eta over dt plus c d eta over dx is constant, 0, not constant, but 0. And so in co-moving frame, if we take Lagrangian derivative d over dt is d over dt plus c d over dx co-moving frame. In a frame moving with speed c. Then we have our equation takes form in that co-moving frame d over dt of c equal to 0, the eta over dt equal to 0, meaning that they both remain constant in co-moving frame. But now we have the same thing, but instead of c, we have a modified c. Now this goes in. This is the corrected non-linearly at speed of frames, which now depends on the wave height. So we plug this also, this goes now into this term here. Right, this substitutes that and go over there. And if you do that, it becomes this and that. Sorry, here is mistake, not d over dx, but d over dx needs to be. And as well, so we see that in order to have describe this nonlinearity of waves, that higher waves propagate faster, then we need to take into account. Then we need to add this kind of term here. Now, what we can do next? With this equation, we can again go to new coordinates in co-moving frame. Now let me do it. You have a more problem here. It just says that it is a Lagrangian derivative, but now let's keep the Lagrangian derivative for later. So I say that I am going to now to a co-moving frame where eta is considered as a function of x minus ct. This is first coordinate, and the other it might still depend on t, right? But if I take like that, then I say that this is the new coordinate, the co-moving frame, and the coordinating normally frame I denote as psi. And in that case, if we do that, then new coordinates d over dt now, d eta over dt. Let us like this one here. Now what becomes this? The d over d eta over dt becomes I think you need to make it, maybe you need to put the plus here, right? If we take now derivative in the new coordinates and the old time derivative in new coordinates, depends on both on the first term and the second term. And so this becomes d eta over dt, which is old coordinate, old time. And here is the new one. So here I take first over d eta over d psi, and then d psi over dt, which is times c, and then plus d eta over dt, and this is a new coordinate. And I think still I need to have to minus here because I need to bring that to the other side. So this was minus, this was minus, and now, no, that was not minus. What was minus was the first term. And then I bring to the left hand side. If you go to the left hand side, and d over d psi is the same as d over dx in old terms. So I can see that in new coordinates, the equation is just d eta over dt. Existing terms now disappears, but that remains plus 1/2 square root of g over h eta d eta over dx equal d psi. Now it is over d psi equal to 0. All right. So what does this term tell us? So to begin with, actually, we can, if we'd like, then we can get rid here of the, let us say that numerical free factor there by renormalizing, for instance, time. If we normalize time so that something t equals t divided by that guy over here, then this coefficient goes away. So I think we did last time exercise how to make equation dimensionless, didn't we? And you had even some homework, I think. No linear oscillator, or did? Oh no. Right. I'm confusing maybe another lecture. Right. So if we introduce key prime equals t and times the reciprocal of it. We divide basically, we divide right sign and cause terms by this factor here. Then this becomes here as 1 divided. And then if we say that t prime is t multiplied by that thing over here, 1/2 square root of t divided by h. Then in new coordinates, equation would be d eta over dt prime plus eta d eta over dxi equal to 0. Agree? Now here we can introduce the Lagrange derivative, because now this was supposed to be height, but again because we have height and speed related to each other, so we have first approximation is v multiplied by h plus eta is constant. Then a, let us say, is constant. Then we can say that v is a divided by h plus eta. So basically that can be linearized. This is a divided by h multiplied plus 1 minus h divided by eta divided by h. So this is certain constant v naught minus eta divided by eta a divided by h squared. So we have v expressed in terms of eta. And they are in linear relationship now. So instead of eta, we can use the same equation, but for velocity instead, if it's convenient for us. And let us say right now, that, in which case we just rewrite this for the speed. dv over dt plus, and now we just got rid of that prefactor, and this becomes v dv over dx equal to 0. Now, this here is a so-called full derivative, a Lagrange derivative, and that we already dealt with, didn't we? Do you still remember Lagrange derivative, use Lagrange derivative? Otto? No. Okay, in that case, I'm pretty much sure we did, but it doesn't harm to do it again. So first, let me write that this because d over dt plus v d over dx is what is called called full derivative or Lagrange derivative, and actually in 3D version of this is d over dt plus v nabla is the full derivative. And then our equation becomes just dv over dt is 0. Lagrange derivative of v is 0. But then what is Lagrange derivative? It's a question. So this is again, actually you won't need to do much. We already did the work. As we did before, remember, we said that if we go to co-moving frame, then in new frame d over dt goes to d over dt plus cd over dx, didn't we? If we go to a frame that moves with speed c, then in co-moving frame derivative is like that. That we just did right now. Now, it is exactly the same thing, but here we substitute C with V. So this thing here is derivative in a frame moving with speed V. But V is the speed of the particle itself, right? So in that, this equation then states that the speed of the particle doesn't change. If we go to a frame that moves together with a particle, its derivative is zero. That's why it is called full derivative or Lagrangian derivative. So it is a speed of a particle in a frame of the particle of itself. Like if you, if we had that Euler equation for fluid flow that was written as Lagrangian derivative of velocity of a particle. This is its acceleration. Now, times rho, this is now Newton's second law. And this becomes volume, this must be equal to force per volume, that is gradient of pressure, equal to zero. So this means that acceleration of a particle is given by pressure gradient. Very simple equation. And right now here we have full derivative of particle. Well, it's not directly fluid speed v, because we did some tricks here. First we had height, and then we said that okay, instead of height we take velocity. Velocity is related to height through a nonlinear term. So it is not exactly right now the particle, but you can interpret it as a particle, the speed of a particle, if you like. So now we obtained equation. Well, basically we obtained equation. Technically, we obtained equation for eta, wasn't it? This thing here. So we obtained equation for eta, but here we can. It's just mathematical expression. We can interpret, say, okay, let eta be speed of something, and then that speed. It was supposed initially to be the height of the wave, but we can instead say that height of a wave like a speed of something. All right. And then this equation in itself is quite somewhat interesting. So let me write it. So just maybe it's more physical for the time being convenient to work with height, which is something you can see. So we have equation d eta over dt plus eta d eta over dx equal to 0. And this is full derivative where speed is eta, the height itself. So if we have initially wave like that, wave pattern on the water, here is the bottom, right? Then these points here move faster, and these move slower, and these move even slower, right? So what happens during the process is that this becomes like that, maybe. And certain moment you will be having wave breaking, meaning that the top caught up the bottom. Right now you have a wave breaking, meaning that at this point here you have different speeds possible. At the same point, you have particles that the top of a wave moves with one speed, bottom moves with other speed. Well, actually, this, of course, is no longer correct because our equation was derived based on the assumption that it is a shallow water, the height is not very high, you can make a approximation, Taylor series. If it's like that, these assumptions are no longer valid. But what clearly remains valid is that the equation, at least at the beginning, the equation is exactly like that. Then again, you can also consider situations where wave breaking can take place. Let us say that you have a sparse gas initially, and then you put into motion with at very high speed, supersonic speed, ultrasonic speed, much higher than Mach number much larger than 1. Then we have here the same wave profile initially. Here is the speed of particle. Here is the coordinate x. And then you will be having wave breaking. It goes something like that, right now. And that, in that case, because here right now we have no complicated assumptions. We have sparse gas, fast separation, we neglect pressure. If we can neglect pressure, every particle moves with constant speed. So this process is totally described by Lagrangian derivative equal to 0, which means that dv over dt plus v dv over dt is 0, as long as you can neglect pressure. And if it's very sparse, you can always neglect, basically. And in that case, here you have particles that are stand, that move left, and that move right. Otherwise, it goes right and that move left. Okay, so you have like a many stream flow over there. No? But if we ask, for instance, now, how is the density of the gas? It becomes infinite at a few points. Here you have infinity. Here you have infinity. Because so why it is infinite? Because initially, let us see. Initially, that point here came from here, isn't it? Oh no, not here. From here. This point here came from here. Okay, that point here came from here. Now, all the particles in between, in this segment here, are now here. In this segment here, but now here it's actually basically infinitely narrow. They were spread over this range here, and now they are spread over infinitely narrow range over there. So it means infinite density, right? Density. So this is called a theory of catastrophe theory. This is called caustic. We are speaking about caustics and catastrophe theory later on a little bit more. For the time being, let us mark it as one thing to discuss later. So singularity that appears here right now.
What is the name?
Caustic. So caustics are something that you might have seen in real life. Raise your hand if you think you have seen caustics.
I don't understand what is caustic.
Yeah.
Rubbers.
Let me. Maybe I can find your video or something. of recording. My laptop is quite slow right now, but maybe I can find some. Okay. The only problem is that Johan cannot see probably, but the rest definitely can see. For Johan, I can just share maybe a link, not to start making. Yeah, okay. Everyone here in the room can see, and let me just share a link for Johan to open in the browser. Oh, I cannot write. It's too long link. It's not exactly what's going on. Okay, here. A little. All right, and now I can share the link to Johan. It said previously the link address was too long. I don't know. So, right.
Aitäh.
What you can see here, what do you think? What is here?
Water, it's reflected by sunlight, or
Yeah, you have water, you have waves on the water, but they are smooth waves, like nothing breaking, not too long, too strong waves. And then you have sun shining, and then this is a light at the bottom, right? So here you can also see something like singularities. Here, those bright lines here are singularities, which emerge exactly in the same region as here. And now,
This was also, if I turn on the flashlight through the water, it will also do that.
yes.
Absolutely.
Right. We can discuss that. I am right now not very prepared to talk more about catastrophe theory, but that is actually interesting thing. We'll discuss a little more, because in catastrophe theory you can distinguish different singularities, and so you can actually classify all the different possibilities for singularities that you can have. Cusps and whatsoever. I need a little bit of prepare to talk you better about it. But here, what we will be having is a caustic. And now let me back normal screen. And Juhan, did you, kas sa said selle lahti, selle lingi?
Jah, sain hästi.
And so if we have water, so what is going on with water? So here you have a surface of the water. Here you have parallel beams coming. And then they bend. So they bend according to reflection law. So they go something like that, and somewhere they converge. And so now if you can plot, and let us do such a thing. As here we have coordinate x. And here we plot a new position of x prime as a function of x. So this here, this ray here, this ray here goes to this position x prime, this x. All right. So we have a certain mapping of x to x prime, and then if we plot here x prime as a function of x. So without water surface, it would be just a straight line. But now we have, the deeper we go, the more convoluted it becomes. That straight line now becomes maybe something like that. Right? And now we have caustics appearing in every place. We have derivative goes to infinity. So here we have going to infinity, maybe here as well, and maybe here as well. Maybe here, yeah. So here we have singularity here, singularity over there at those positions. Sorry, I think I did a little. Let me fix it. X. It is a uniquely defined function of x. For every x, we have x prime. I was too sloppy when I drew the curve. For every x, we have x prime, but for every x prime, we can have different x's. Right here, for this position here, we have a different beams that arrive here. So we have now something like that. And now our caustics are here. So here is one caustic. We have a range of x's going to certain x prime. Here we have another caustic. Again, range of x's going here. And here we have another caustic. And so these are these bright lines because you have a lot of light going over there. In the same way as you have in the case of wave breaking. It's very similar, mathematical actually, those two things, right? And if you were to study more the problem of wave breaking in the case of that sparse gas, then we can say, okay, we neglected pressure, but maybe we can still try to take into account pressure as well. And then what happens? Then maybe the pressure is strong enough to stop the wave breaking. And then it's another problem that you can study. That actually, if any one of you is interested in it, that problem actually has been this year's Physics Cup competition problem number 3, I think. So whenever you happen to be interested in that, then you can open that program. It has also hints. You can try solving it. So physicscup.ee, and the solutions are not yet published, but they're going to publish some within a month or so. Problem number 3, Physics Cup, you can try solving it. Basically, the statement of the problem is exactly that you have sparse gas, initial velocity is very big, Mach number very large, and you are asked under which condition the wave breaking stops. And that's exactly when you need to. It is not very easy problem, but interesting nevertheless. All right. So where were we? We had that equation over there, and this is called simple wave equation, and this leads to wave breaking. And in most cases, wave breaking is not physical because if we're going to say this describes water in shallow water, then as soon as it goes too steep, equation no longer remains valid because the assumptions we made remain applicable. In other cases, it remains valid and you can still work with it. But now going back to shallow water waves. So we have this equation over there, and then what might stop wave breaking? And the answer is exactly that dispersion what we have. Because if we have a wave profile like that, and then it evolves into something like that. And then if you think about local wave vector, so you, first your wave vector was long, right? No, wavelength was long, lambda. This, let us say, this quarter of wavelength, like half of wavelength, right? But now, here, half of wavelength became very short. This was supposed to be length. Now half of the wavelength becomes very small. From maximum to minimum. And so it means that a wave vector k is effectively grew. K became bigger. And then if we think about our dispersion thing, so this will now also start affecting the how a wave behaves. So actually, we had the negative dispersion. I think it anyway. So dispersion now will smooth it out. Dispersion term in the equation. But they still have combined two terms. But this is now, if k becomes bigger, then dispersion term becomes important. We say that we start with long wave and dispersion is not very important because dispersion was as a correction, right? It was Taylor expansion term. But now, because k become bigger, that relative importance of dispersion term became bigger, right? So it was not important before, but now it becomes. And so what it does out, it stops the wave breaking. The dispersion term now can stop the wave breaking. And to work it out, so now we can bring terms together. So we have this equation on the one hand side. Remember, this is in a co-moving wave, a frame which moves with the speed of linear wave. We went to a frame which moves with that speed c, right? In that frame, we have this equation. Equation in a co-moving frame looks like that. And then we say that this has wave breaking, but this means that k wave vector grows, and we need to now take into account the dispersion. But for dispersion, we have something over here. So this is what you want, equation what you would have if you would like to take into account dispersion. First term that comes into play. So there are other terms as well. If it grows even bigger, as the dispersion importance of dispersion, then you will have higher orders as well. But for the time being, it is first thing to take into account this system here. And so now let us rewrite. So I think we renormalized time already, or we changed our t to certain t prime and to have a coefficientless equation. Now, so we cannot renormalize time again, but we can renormalize coordinate x, and so we can get rid of this. Rid of this if x prime equals x divided by certain b, let us say, right? If we renormalize x prime, introduce x prime instead of x in the same way as introduce t prime instead of t, then we can get rid of this prefactor here. And so it becomes just a cubic derivative. And so bringing all what we have together, our equation becomes dv over dt plus v dv over dx. This is a full derivative thing. And then the expression term dqb over dx cube equal to 0. Now we have both nonlinearity and dispersion. And here we have dispersion. And what can we do with this? This is first, this equation is called Korteweg-de Vries equation, or shortly KdV. Korteweg-de Vries equation. And it is quite famous equation. Why? Because it's quite universal. And now, can you tell me why it is a universal equation? Like if you have oscillations, the equation that you mostly use is linear oscillator, harmonic oscillation, right? And we say it is also quite a bit universal because now anyone can finish why it is considered universal equation. Why harmonic oscillation equation is a universal one, which is very often applicable. Even so, it is very simplified equation, like doesn't take into account nonlinearities and things like that. See, Markus.
I'm not sure I quite understand, but so why does the harmonic oscillator like describe?
Why people use always harmonic oscillator whenever you have some oscillations?
I wonder that myself.
Because they don't know anything else, right? It's quite possible cause, right?
I thought maybe it's like.
Okay, the reason is if you take arbitrary force F as a function of displacement x, right? Then you can always linearize it. F is equal to certain F naught plus certain kx plus certain p x square, right? Taylor expansion, basically. Now, if it's Taylor expansion, so if you have small oscillations, then neglect terms with higher order of smallness. Which means that the x square is going to be neglected, right? You can always, and then F naught is 0 because you have equilibrium, right? At equilibrium, F naught equal to 0. And that's why, because if you have almost always, if you take small oscillations, you can neglect this guy over here. Exception is when this is exactly 0. Only this doesn't work. If k is exactly 0, right? in that case, you need to take next one in order to have some meaningful. Then again, you have what makes you oscillating. You still need to have equilibrium. So if you take this px squared, then it's no longer stable, right?
What is written there? Neglect terms with higher
order of smallness. I think order is missing. Terms with higher order of smallness. Order of small parameter. You have always a small parameter. And you make it maybe, okay. Or in terms of potential, if we have u of x, so that, or v of x. V of x, so that f is minus dv over dx, all right? And then we say that v is certain v naught plus dv over dx multiplied by x plus d square v over dx square 1/2 x square plus 1. If we have a certain characteristic scale L, let L be a characteristic scale, and then dv over dx is certain of the order v over L, d square v over dx square is v over L square, and so on. And so relative importance of terms now. We have this term here. This here is v divided by L times x. That term here is v x square L square, and so on. So our terms are in the order of nth term as v and x over L to the power of n. Our small parameter epsilon equals x divided by L is a small parameter. Now, this is first order smallness. First order of smallness. This is second. Here is third, and so on, right? So, because x divided by L is small, each next is much smaller than the previous one. And we can just stop at a certain point and neglect everything else which is too small. And now, if we have equilibrium, then this term is 0. Equal to 0 at equilibrium. So this goes away, this remains. And normally we won't need to take anything else if we have small parameter epsilon, right? And that's why you have with the first non-vanishing term. We have v equals v naught plus 1/2 e square v over dx square multiplied by x square, and that gives us a harmonic oscillations. And that's why a harmonic oscillation is very universal. Whatever system you have, as long as you won't have very unlikely case that that term there, quadratic term is exactly 0, then you will be having harmonic oscillation. Now, I think I gave that to undergrad students, but you can try just for fun, because we arrived at this point here.
In the blue was written there.
Harmonic oscillations.
No, I mean the whole thing, so.
So with the first non-vanishing term, our equation becomes yeah, right. So as a homework, you can try studying oscillations in this case. You have a spring, mass, another spring, and these springs are not stretched. So here F is Kx. Here is also F is Kx. And now you consider oscillations in this direction, right? And the question is, let us say, how does a period depend on oscillation amplitude? This is a case when actually this term here is exactly zero. Can you see it why? If you had a small displacement here like y, right? Then x equals square root of L square plus y square. L is the non-stretch length here of the spring. Minus L. A normal length was L, and now it is square root of L square plus y square. So this approximately equals to, once you do the Taylor expansion, it becomes y squared divided by 2L. Right? You bring L before the braces. Here is y squared divided by L square. You take 1 plus x is 1 plus x over 2. Square root of 1 plus x is square root of 1 plus 6 is, okay. So do I need to do it more in detail so it's clear now? Okay, so this equals this equals L square root of 1 plus y squared divided by L square minus L equals L1 plus y squared divided by 2L square minus L equals y square divided by 2L. Right? And so now our displacement itself is quadratic. Our deformation is quadratic in displacement. And because of that, our potential energy, V is Kx squared divided by 2. And if we plug in that x in here, then it becomes K y to the 4th divided by 4L. And now here you have 4th order potential. And now you can no longer linearize, but this very exceptional case, right? So, one question is how will oscillation look like right now here? Now, you might have, I have another homework for you today, but how much time do we have? Okay, enough. So I have another homework, but this is not very difficult homework. So fine. Let me find homework one. I don't want to see him saying again that it is too much work at home. one time understood that he struggled a lot, but he was very brave and he finished it regardless.
You don't need to make an exception.
No. I just because I think you are. If you are struggling as I'm struggling as well, and I want us to keep things reasonable.
Well, sometimes you say it's easy, then it takes me like 10 pages anyway, so.
All right.
So, yeah.
I hope not, yes. So, fine, homework. One. Find period t at a function amplitude a. How period depends on amplitude. And the fun thing here is that actually, if amplitude goes to 0, period goes to infinity. Like a pre-announcement, it should be something like 1 divided by a. Now, how do you solve it?
Wait, first, what is written again? I can't read.
Sorry?
What is written? How?
How period depends on amplitude a? Basically, I can sketch you how you solve it. You take total energy is conserved, right? So we have my dot squared divided by 2 plus ky to the fourth over 4L is a constant. It is the total energy E, right? From here, you obtain y dot as a function of y, right? From here, you obtain dy divided by zfy is dt. And from here, you obtain d is integral of dy over f of y. So that's how you obtain it. Now you obtain here an integral, and now actually, even without taking the integral, you can make it dimensionless and see how it depends on parameters. So now make it dimensionless by y prime equals y times certain whatever. Certain whatever, something like a capital, right? You choose a capital such that the integral becomes dimensionless. It does not contain any parameters, only integral. And only the integral y prime. All right, here bounds. Let me do more properly. Here, period is full period once it goes back. It starts at amplitude at the position y is minus a and goes to a, right? But this is half of the period. So full period you multiply by 2, right?
It's gonna be inverse of it.
Sorry?
It's gonna be inverse of amplitude, which is not good.
Well, it is, yeah, time will be inverse of amplitude, yes. Which means that probably if you take very small amplitude and all friction and things like that, it's difficult to, if you want to verify it experimentally, it's very difficult to make very small amplitude, isn't it?
Mm-hmm.
But yes, that's how it behaves. It's also, you can understand qualitatively why, because if you make very small amplitude, tension in the spring is very, very small, and there is almost no returning force, it almost remains at place. So it's, you kind of can understand that it will be very slow, right? There is actually one case when we had such another situation, maybe more physical. We had a mathematical pendulum, a physical pendulum, like a solid something oscillating, right? You all know what is physical pendulum, right? And then there was a magnet fixed to this. And then there was another magnet which approached it. And then if you approach the pushing magnet, Venus, then at certain position, it exactly compensates is normally the potential curve is parabolic, but if you put very close to it, it will be upside parabola, like unstable, magnet is pushing away. And it's clear that in between there is a position of the magnet where it becomes exactly, the quadratic term goes away exactly. And so like in that experiment, you are moving that magnet and found the position when it is exactly goes away, and then you can study really experimentally how the period depends on that. And yeah, it does work. If you do it properly, it does work. Anyway, so we were discussing actually completely different thing. We were discussing the question why KdV equation is universal and appearing in many places. And then I was asking why harmonic oscillation is very universal. Normally, actually, I think it is usually mentioned during your first undergrad studies. I don't think our guys here from Caltech have been mentioned because they usually just told to look into textbook, but the others might have heard that during their undergrad course that harmonic oscillation is universal for small oscillation because you can linearize around that, right? Anyway, now going back to KdV equation. Question is, let me write it again. KdV is dV over dt plus v dV over dx plus d cube dV over dx cube equal to 0. And this is also quite universal. And now the question is why? Why is this universal? Can any of you now explain why this is universal? Exactly the same reason that you have always the first terms that go into play. So first non-vanishing terms. So let us say first here, this guy here. Now that was supposed to be c of propagation speed. Then what we did, we can say that actually c depends, it has a certain nonlinearity. You said that it was height, and then you said that speed is a function of height. And then, but then Justin already noted h went back from h to v. But then if this is a certain function of v, then we can say that this is c naught plus dc over dv multiplied by v plus d square c over dv square times v square and plus 1. Okay, and for the case of small amplitude, this is the first non-vanishing. Vanishing if v our small parameter is v, that is much smaller than 1. Right? So we neglect those. The main non-vanishing nonlinear term is this. Now we got rid of that by moving to co-moving frame. So that was not important because we were able to get rid of it by changing coordinates. And so that guy here remains. And that's now here, right? Now regarding the second term. That was the first non-vanishing dispersion term. Because we had V phase is a certain function of K, right? But we assume that the speed does not depend on direction of wave. Like we have isotropic medium. Isotropic medium. Then we have the phase depends only on square, like only doesn't depend on the sign, but only on the modulus of wave vector. Left and right propagating waves are the same. So now our equation becomes omega square over it's just omega over k. Omega over k is f of k is approximately f naught plus d square f over d k square times k square, so that omega equals f naught k plus d square f over d k square and k cubed. And now this goes to d over dx, and this goes to d cube over dx cube, right? And this is the non-dispersive term. This is the first non-vanishing dispersive term. Yeah, going back to oscillators. So if there is a reason why you would like to take into account nonlinearity, one reason is that you have exactly vanishing linear force term like that homework I gave you. The other reason is that actually you need to know how depends frequency on the amplitude. Like if you have a resonance, you have forcing resonance, force which oscillates periodically, and then if you had a strict linear oscillator. So if your force is exactly resonant with that oscillating frequency, then you would go to infinite amplitude oscillation, right? But in real life, if your frequency of your oscillator depends on the amplitude, it is no longer resonance for larger amplitudes. So in some cases, depending what you do, you might still want to take a second non-vanishing term as well. The first non-vanishing term, first term that gives you the effect you're looking for. Like if you want to have for nonlinear, you want to have for oscillators study resonance, then you would need to actually take into account the possibility of period depending on amplitude, and then you would need to take the other term, the next term as well. Like here, actually, this is the first non-vanishing term, right? Now we take second non-vanishing term because this gives us something that first didn't have. In the case of oscillator, if you take just the quadratic potential, this doesn't give you dependence of amplitude on of the period on amplitude. Now here, this here gives us dependence of speed on the wave vector. That we need to stop the wave breaking, right? We need it, and it's like physically important now. It's not that something we are wondering what, but exactly in the same way as the resonance is stopped by frequency shift. In the case of oscillator, here we need that to stop the wave breaking. Should I write down also the oscillator thing here, what we discussed right now? So, suppose we have mx double dot equals minus dv over dx, approximately equal to k minus kx, then omega is square root of k divided by m, and consider mx double dot plus dv over dx equals cosine omega t. Right? This is resonant. Here, at the resonance, amplitude goes to infinity, right? But in reality, it doesn't go to infinity, right? So now, to stop this, we need the next largest term in V in Taylor expansion of V of X, right? Then P becomes a function of amplitude like in the homework. And so this shifting away from resonance. Exactly the same way. Exactly the same way. Way d that k cube term is the first term, the largest term, that stops the wave breaking. Okay, so that's why it is universal. We have both terms are the first. This is normally and usually it's the first terms that you need to take into account if you want to first case take into account nonlinearity, and nonlinearity is important because nonlinearity now brings you to wave breaking, and dispersion because nonlinear dispersion because linear dispersion is important because it can stop wave breaking. It's kind of a strange show that you want to have wave breaking and then you want to stop it, but regardless. So as a result of those two things, what appears to happen is that now you will be having solutions in the forms of so-called solitons. So KdV equation, KdV of solitons. So what are solitons? Solitons are waves that can propagate without changing shape. Well, normal sinusoidal in the linear world, they are also that. But in the case of nonlinear equations, it's a little different. So you have a certain phase and then that propagates with propagating. And now let us see how it works out in the case of KdV equation. But maybe before we go to KdV, all right, okay, we're gonna equally well go. We're so sorry. So our equation is now dv over dt plus v dv over dx plus d cube v over dx cube equal to 0. Now we have a solution that propagates with a constant speed. Then it means that we can go to Coulombic frame again. Now let us go to a frame that moves with speed u. In that case, we expect that it is stationary. We go to a frame of speed u, so that d over dt becomes minus d over du, minus u d over dx. You're already familiar with this procedure, so I think I can skip a little details here. Minus u d over dx. All right. In that case, it would be plus d over dt prime, but this equals to 0 because we expect stationary solution in going frame. And so our equation becomes now v minus u dv over dx plus d cube v over dx cube equal to 0. Right? Because the first this term here went to minus u dv over dx. Right? Now what we're going to do now we need to solve this, right? Luckily, we have now only one variable, so this is ordinary differential equation now. It was a partial derivative before, but now it became ordinary. Good thing is that we can first integrate it by x. Integrate by dx, and then we obtain v square over 2 minus uv plus d square v over dx square equals constant. And now what we do next is that we interpret x as a type. In that case, this becomes acceleration. And then we can introduce v as an integral of that. V of v is integral of v squared divided by 2 minus uv dv equals v cubed over 6 minus uv squared divided by 2. And then we have a particle in potential, and v is a displacement of a particle. V is a displacement. Right? Acceleration and gradient of potential. Now we can try thinking what does the potential look like. Potential first we have at large v it goes this dominates. At small v this dominates. So it first goes, parabola goes down and then turns up. Something like that. Take it up here, probably. And now we can also think about find position. So if C0 is B0, but now this non-zero point, we divide this by B square, and then I obtain at this point here, we have V over 6 minus U over 2 is 0, meaning that V is 3U. So here is 3U. Now we can calculate also this point here. And this turns out to be 2U because, well, we take derivative. 3 V squared divided by 6 minus UV equal to 0. From here you obtain that first V 0. This is also extremum point, but then we have from here V is 2U, right? And now what I can conclude from this is that if our particle, this was like oscillator, also non-linear oscillator, it is clear that if we take our particle here at the bottom, it will oscillate here back and forth, right? It can oscillate back and forth at the bottom, but it can also start from here. Let me draw it in a different color maybe. It can start from here and then roll down, roll up, and then turn back because now it has now enough kinetic energy, velocity becomes 0, and then go back and roll up again here, right? Is it clear what it can do? And stay here infinitely long because this is a stationary point. So now that a green curve becomes solution like that, V as a function of time t, so it starts with 0. Let me make axis black. And the curve itself green. So we have here, and then goes up and goes like that. And we know that the maximum point actually is 3U, right? This is 3U. Okay? This is one possibility. But there are intermediate possibilities as well. There is a possibility like wave going like that, back and forth. These are nonlinear waves. The closer you go to here, the longer it becomes. These are known as called nidal waves. So the purple one corresponds to something like that. It goes up almost like solid because it almost reaches that point and then goes down, but it doesn't go to infinity, but after a long time goes again. Right? Something like that. Waves. And this is a solid. Now, this shape actually can find it. You can integrate. So how you do it? Well, we have this equation here. This one here, right? So for soliton, right hand side is 0, right? Because we start from this point here. So we have v squared divided by 2 minus uv plus v second derivative is 0. And then there is a energy conservation law. Well, let me make here a little room for this math. I'm still not sure I can finish everything what I wanted for today. If not, then we just need to continue next time. So this is from here, equation of motion, I can go to energy conservation law, in which case it becomes kinetic energy is V prime squared divided by 2. And potential energy is integral of that. So formally, okay, maybe you can do it more formally. So this is the equation what I need to solve, right? And here we can look for new variable v prime dv over d x is our new variable. This is something like let us say that w. W, and then we have here d square v over d square v over dx square is dw over dx, but this here is dw over dv and dv over dx, right? And dv over dx is another w. So it is w w over dv is 1/2 d square over d over dv of the w square, right? And then we can put it in here and integrate once by v, right? We have integral of v squared over 2 minus uv dv plus 1/2 w square equals constant, right? And then we obtain from here that if we take integral, we have v cubed over 6 minus uv squared over 2, the same familiar potential already, plus 1/2 d v over du, v over dx, the speed squared, equals, and in our case, for Soliton it is 0, right? And from here we can obtain dv divided by let us separate variables now. V square and v minus u. And here we put 6 and equals three. Something's not right. If I take 1 to 6 over here, so it becomes minus 3u. It have been easier to just delete it and write it again. Minus 3u. Equals 3x. Is it right? X, no, factors are wrong. So it happens when you try to do much thing in your head. So I separate here dv, take square root. As I already forgot square root. Let's do it wrong way. Okay. dv over dt equals v cube over 3 uv square. V square u minus v over 3 I multiplied everything by 2, so this 2 goes away, 3 remains. And then from here I can obtain dv divided by square root of v square root of u minus v over 3 equals dx. Basically, you can take the integral now, if you are smart enough. And if you do that, you obtain here the shape of a soliton. And the shape of a soliton appears to be hyperbolic seconds. So v equals something like 3 u hyperbolic seconds, which one divided by hyperbolic cosinus of x. But then x divided by u probably. Let me just
Attention, please. Due to an emergency situation, we ask everyone to leave the building immediately through the nearest exit.
Okay, actually, we are all basically finished. Just let me write it down and let us continue next time.
Attention please. Due to an emergency situation, we ask everyone to leave the building immediately through the nearest exit. Attention please. Due to an emergency situation, we ask everyone to
3u is secant squared and x square root of u. All right. So now
please. Due to
you obtain soliton.
Situation, we ask everyone to leave the
And how those solitons behave and why they are also an important thing, interesting thing. We continue next time. And next time we will be also learning then about the so-called inverse scattering method to solve this gated equation. Inverse scattering method. It appears that also this equation in partial derivatives is nonlinear. It can be solved exactly. And how it is done, this actually is quite important point, and because the method what was revised, it appears to be quite powerful and universal for other equations as well. So we'll go through briefly next time.
Attention please.
So because we didn't go reach inverse scattering point, you are lucky you got only one homework. Because another homework was actually to show something quantum mechanically. For the inverse scattering method to work, you need to have full derivative of one operator to be zero in terms of quantum mechanics. But that's again, yeah, next step. That would be would have been your second homework to show that this full derivative is zero. Ja Juhan, me peame nüüd siin.
Attention please. Due to an emergency situation, we ask everyone to leave the